Black holes are among the most mysterious and fascinating objects in the universe. They captivate our imagination and challenge our understanding of physics, offering a glimpse into the extremes of space, time, and reality itself. From their immense gravitational pull to their enigmatic singularities, black holes represent the ultimate frontier in astrophysics. But what makes black holes so unique? What happens to anything that ventures beyond the event horizon, the boundary where escape becomes impossible? Could they hold the key to unlocking the universe's greatest mysteries, such as the nature of space-time, the origins of galaxies, or even the possibility of other dimensions? In this video, we'll journey into the heart of black holes to explore their profound significance in science. We'll uncover how they form, how they shape the cosmos, and the bizarre phenomena they create. Black holes are some of the strangest and most fascinating objects in the universe. At their core, they are regions of space where gravity is so strong that nothing, not even light, can escape. This immense gravitational pull is created by a massive amount of matter being squeezed into a tiny space, resulting in a density so extreme that it warps the fabric of space and time itself. The defining feature of a black hole is its event horizon, the boundary beyond which escape is impossible. Once something crosses this invisible line, it is drawn irreversibly toward the black hole's center, or singularity, where the laws of physics, as we know them, break down. This singularity is a point of infinite density, a concept that defies our understanding of how matter behaves. Black holes come in different types and sizes, depending on how they are formed. Stellar black holes, which are the most common, form when massive stars exhaust their nuclear fuel and collapse under their own gravity. These black holes typically have masses several times that of the Sun. At the other end of the spectrum are supermassive black holes, which are found at the centers of galaxies, including our own Milky Way. These titanic structures can have masses equivalent to millions or even billions of suns, though their exact formation process remains one of astronomy's biggest mysteries. There are also intermediate black holes, which fall between stellar and supermassive in size, and primordial black holes, which are hypothetical remnants from the early universe. These tiny black holes, if they exist, would have formed shortly after the Big Bang and might provide clues about the origins of the cosmos. While black holes cannot be observed directly, since no light can escape from them, their presence can be detected through their effects on nearby objects. For instance, we can observe stars orbiting rapidly around an unseen mass, or detect high-energy X-rays emitted as gas and dust spiral into the black hole's event horizon. Black holes are much more than gravitational traps. They are engines of cosmic transformation, shaping the universe around them. To truly understand their mysteries, we must first explore how they come into existence. The formation of black holes is a dramatic and powerful process, deeply tied to the life cycles of stars and the violent dynamics of the universe. The most common type of black hole, a stellar black hole, is born from the death of a massive star. Stars are essentially giant nuclear reactors, fusing hydrogen into helium in their cores and generating immense outward pressure from this energy. This outward pressure counteracts the force of gravity trying to collapse the star. However, when a massive star exhausts its nuclear fuel, it loses this delicate balance. Without the energy to resist gravity, the star's core collapses under its own weight, compressing the matter into an incredibly dense state. For stars much more massive than the Sun, this collapse creates a black hole, leaving behind an event horizon that marks the point of no return. The process is even more spectacular in a supernova explosion. As the core collapses into a black hole, the outer layers of the star are violently ejected into space, enriching the cosmos with elements like carbon, oxygen, and iron, materials essential for life as we know it. While stellar black holes are the result of individual star deaths, supermassive black holes found at the centers of galaxies are a far greater enigma. These giants can have masses millions or billions of times that of the Sun, but their formation remains a mystery. One theory suggests they grow from smaller black holes by consuming surrounding matter and merging with other black holes. Another possibility is that they formed directly from massive clouds of gas in the early universe, collapsing under their own gravity without ever becoming stars. There's also evidence suggesting that black holes can merge to form larger ones. When two black holes spiral toward each other and collide, they create an even more massive black hole. This process emits powerful ripples in space-time, known as gravitational waves, which scientists have detected using observatories like LIGO and Virgo. A less commonly discussed possibility involves primordial black holes, which may have formed in the chaotic moments following the Big Bang. These black holes would be much smaller than their stellar or supermassive counterparts, with some theorized to be as small as a grain of sand. If they exist, primordial black holes could provide valuable insights into the conditions of the early universe, and even account for some of the mysterious dark matter that makes up much of the cosmos. Regardless of how they form, black holes represent the ultimate collapse of matter and energy, creating objects so extreme that they stretch our understanding of physics to its limits. Their creation is only the beginning of their cosmic story, as their influence extends far beyond their boundaries. What happens inside a black hole is one of the greatest mysteries in astrophysics. Once an object crosses the event horizon, the point of no return, it is subjected to extreme gravitational forces and enters a realm where our understanding of physics begins to break down. The most well-known phenomenon near a black hole is spaghettification, a process where the immense gravitational pull stretches and compresses objects into long, thin shapes like strands of spaghetti. This occurs because the gravity at the black hole's event horizon is not uniform. For instance, if you were falling feet first into a black hole, the gravitational pull on your feet would be significantly stronger than the pull on your head. This tidal force stretches your body to the breaking point as you approach the singularity. At the center of a black hole lies the singularity, a point where the gravitational force becomes infinite and space-time curves infinitely. The laws of physics, as we know them, no longer apply here. General relativity, which describes gravity and the large-scale structure of the universe, predicts the existence of singularities, but quantum mechanics, which governs the behavior of particles on the smallest scales, cannot reconcile with this prediction. This conflict highlights one of the biggest challenges in modern physics, unifying general relativity and quantum mechanics into a single theory. Inside the event horizon, time and space behave in ways that defy our everyday experience. Time slows down dramatically near the event horizon, a phenomenon known as time dilation. To an outside observer, an object falling toward a black hole appears to freeze in time and never fully crosses the event horizon. However, from the perspective of the falling object, time proceeds normally and it continues its journey toward the singularity. What actually happens at the singularity remains unknown. Some theories suggest that matter is crushed into an infinitely small point. Others propose that the singularity may not even exist, and new physics, still undiscovered, might provide an explanation. There's also speculation about whether black holes could act as gateways to other regions of the universe or even to other universes. The concept of wormholes, also known as Einstein-Rosen bridges, arises from solutions to Einstein's equations of general relativity. These theoretical structures could connect two separate points in space-time, potentially allowing travel between them. However, the existence of stable wormholes remains purely hypothetical, as they would likely collapse too quickly to be traversable. Some scientists even propose that black holes could serve as the seeds for the formation of new universes. According to this idea, the extreme conditions inside a black hole might trigger a Big Bang in another region of space-time, creating an entirely new universe with its own laws of physics. While much of what happens inside a black hole remains speculative, studying these mysterious objects pushes the boundaries of our knowledge and forces us to confront the limits of our understanding. Black holes challenge our most fundamental ideas about space, time, and the very fabric of reality. Black holes are far more than isolated cosmic phenomena. They play a critical role in shaping the structure and evolution of the universe itself. From their gravitational influence on nearby stars and gas to their connection with galaxy formation, black holes are central to the dynamics of the cosmos. At the heart of most galaxies, including our Milky Way, lies a supermassive black hole. These colossal structures, with masses millions or billions of times that of the Sun, anchor the galaxies they inhabit. Scientists believe that supermassive black holes and their host galaxies evolve together in a symbiotic relationship. As gas, dust, and stars are drawn toward the black hole, they heat up and emit enormous amounts of energy, creating active galactic nuclei or, in extreme cases, quasars, some of the brightest objects in the universe. This energy can regulate star formation within the galaxy, influencing its long-term development. Black holes also act as cosmic sculptors. As matter falls into a black hole, some of it is ejected at near-light speeds in powerful jets. These jets, made of high-energy particles, can extend thousands of light years into space, disrupting the surrounding interstellar medium. This process redistributes matter and energy, shaping the environment and influencing the formation of stars and planets over time. In addition to supermassive black holes, stellar black holes also play a key role in their local environments. When they form after a supernova explosion, they release heavy elements into space, elements that later become the building blocks for new stars, planets, and even life. The remnants of these stellar deaths help enrich the universe with the chemical diversity necessary for complex structures to form. Another fascinating connection between black holes and the universe's structure involves their role as gravitational lenses. The immense gravitational pull of a black hole bends light from distant objects, creating a phenomenon known as gravitational lensing. This effect allows astronomers to study objects that would otherwise be hidden behind massive celestial structures. In this way, Black holes act as natural magnifying glasses, revealing more of the cosmos than we could see otherwise. Furthermore, black holes are deeply connected to the mysterious concept of dark matter, the unseen material that makes up about 85% of the universe's mass. While dark matter's relationship with black holes is still poorly understood, some theories suggest that primordial black holes formed shortly after the Big Bang could account for some of the missing mass attributed to dark matter. Studying this connection might one day unlock new insights into the nature of the universe's most elusive components. Black holes, once thought of as cosmic anomalies, are now recognized as essential players in the grand design of the universe. By shaping galaxies, recycling matter, and acting as gravitational powerhouses, they influence the cosmos on both small and large scales. Understanding their role helps us piece together the vast and complex puzzle of how the universe came to be and continues to evolve. One of the most perplexing mysteries in modern physics is the black hole information paradox, a problem that has baffled scientists for decades. At its core, the paradox raises a simple, yet profound question. What happens to information when it falls into a black hole? In physics, information refers to the fundamental properties of matter, like the spin, charge, and position of particles, that describe its state. According to the principles of quantum mechanics, information about the state of a system can never be lost, even if the system undergoes extreme changes. However, black holes seem to defy this rule. When matter falls into a black hole, it crosses the event horizon and is pulled toward the singularity, where it is crushed into an infinitely dense point. From an outside observer's perspective, that matter and the information it carries appears to disappear forever. Yet this violates the fundamental laws of quantum mechanics, which state that information must be preserved. This conflict between quantum mechanics and general relativity is at the heart of the information paradox. In 1974, Stephen Hawking made a groundbreaking discovery that added another layer to this puzzle. He theorized that black holes aren't entirely black. Instead, they emit a faint radiation, now known as Hawking radiation, due to quantum effects near the event horizon. Over time, this radiation causes the black hole to lose mass and eventually evaporate. If a black hole completely disappears, what happens to the information about the matter that fell into it? Does it vanish along with the black hole? Or is it somehow encoded in the radiation? This question has led to intense debate among physicists. Some suggest that the information is permanently lost, a conclusion that challenges the foundations of quantum theory. Others argue that the information might escape in some form, possibly encoded within the Hawking radiation itself. However, deciphering this encoded information, if it exists, remains a monumental challenge. There are also more exotic solutions. Some physicists propose that black holes might store information on their event horizons, like data on a two-dimensional surface. This idea, known as the holographic principle, suggests that the three-dimensional information inside a black hole could be projected onto its two-dimensional boundary, preserving the information in a way that aligns with quantum mechanics. Another speculative idea is that black holes might act as gateways to other parts of the universe, or even to other universes. In this scenario, the information might not be lost, but instead transported elsewhere, beyond the observable universe. While this concept is highly theoretical, it opens the door to fascinating possibilities about the nature of reality. The black hole information paradox remains one of the most intriguing unsolved problems in physics. Resolving it could lead to a deeper understanding of the relationship between quantum mechanics and gravity, potentially unlocking a unified theory of physics. For now, it continues to inspire debate, research, and the pursuit of answers to the universe's greatest mysteries. Black holes have long sparked speculation that they could be more than just destructive cosmic phenomena. Could they in fact serve as gateways to other parts of the universe, or even to entirely different realities? While the idea might sound like science fiction, some theories in physics suggest it could be possible. The concept of black holes as wormholes or Einstein-Rosen bridges comes from solutions to Einstein's equations of general relativity. In these solutions, a black hole could theoretically connect two distant points in space-time, forming a tunnel-like structure. If stable wormholes exist, they could allow matter or even information to travel instantaneously across vast cosmic distances or potentially link entirely separate universes. However, there are significant challenges to this idea. First, wormholes, if they exist, are likely unstable. The immense gravitational forces inside a black hole would cause the wormhole to collapse almost instantly, preventing anything from traveling through it. Second, to stabilize a wormhole, scientists hypothesize that an exotic form of matter with negative energy density would be required, something that has yet to be discovered or created. Another intriguing possibility is that black holes might lead to baby universes, new regions of spacetime that branch off from our own. Some cosmologists propose that the extreme conditions inside a black hole's singularity could mimic those of the Big Bang, creating the conditions necessary for a new universe to form. In this scenario, the black hole in our universe would act as the parent of the new universe, with the event horizon serving as the boundary between the two. This idea, while speculative, has gained traction in theoretical physics as a potential explanation for how universes could emerge. Some theories also suggest that black holes could provide insights into higher dimensions. According to string theory and related frameworks, our universe might be one of many brains floating in a higher dimensional space. If black holes interact with these extra dimensions, they might reveal hidden aspects of the cosmos or even serve as portals to other dimensions. This could help explain phenomena that currently defy our understanding of physics. Despite the theoretical appeal, there's currently no direct evidence that black holes connect to other universes, dimensions, or points in space-time. These ideas remain speculative, but are deeply rooted in the quest to understand how gravity, space, and time interact at the most extreme scales. Black holes challenge the limits of our knowledge and push the boundaries of what's possible. While the idea of them as gateways to other realities remains unproven, exploring these possibilities inspires new ways of thinking about the universe and its infinite mysteries. Studying black holes may seem impossible at first glance, given that no light or information can escape their event horizons. However, scientists have developed ingenious methods to observe their effects and uncover their secrets. By studying the interactions between black holes and their surroundings, researchers have made remarkable discoveries about these enigmatic objects. One of the primary ways to detect and study black holes is by observing their gravitational influence on nearby objects. For example, if a black hole is part of a binary system with a star, It can pull matter from the star into a swirling disk of hot gas called an accretion disk. As the gas in the disk spirals closer to the event horizon, it heats up to millions of degrees and emits high-energy radiation, such as X-rays. Observatories like NASA's Chandra X-ray Observatory and ESA's XMM Newton have been critical in detecting these emissions and identifying stellar mass black holes. Another breakthrough in black hole research came with the detection of gravitational waves, ripples in space-time caused by massive cosmic events such as black hole mergers. In 2015, the Laser Interferometer Gravitational Wave Observatory, LIGO, made history by detecting gravitational waves for the first time. This groundbreaking observation confirmed a prediction of Einstein's general theory of relativity and provided direct evidence of black hole collisions. Since then, both LIGO and the Virgo detector in Europe have identified dozens of gravitational wave events, offering new insights into the behavior and properties of black holes. In 2019, black hole research reached another milestone when the Event Horizon Telescope, EHT, captured the first ever image of a black hole. This iconic image showed the shadow of a supermassive black hole at the center of the galaxy M87, surrounded by a glowing ring of light from its accretion disk. The success of the EHT, a global network of radio telescopes, demonstrated the power of international collaboration and innovative technology in studying phenomena that were once thought to be unobservable. Scientists also use computer simulations to model the behavior of black holes and their interactions with nearby matter. These simulations allow researchers to explore scenarios that are impossible to replicate in a laboratory, such as the dynamics of black hole mergers or the effects of extreme gravitational fields on light and time. By comparing these simulations with observational data, researchers can test theories and refine their understanding of black holes. Future missions and technologies promise to revolutionize black hole research even further. Projects like the Laser Interferometer Space Antenna, LISA, a space-based gravitational wave observatory, aim to detect waves from supermassive black hole mergers and other extreme events. Meanwhile, advancements in telescope technology will provide even sharper images of black hole environments, potentially revealing new details about their structure and behavior. Despite the challenges, the study of black holes continues to push the boundaries of human knowledge. By combining observational astronomy, cutting-edge technology, and theoretical physics, scientists are unraveling the mysteries of these cosmic titans and gaining deeper insights into the universe itself. Despite the incredible progress made in understanding black holes, they remain one of the most enigmatic phenomena in the universe. Many questions about their nature and behavior remain unanswered, and ongoing research aims to shed light on these mysteries. One of the most pressing questions is about the formation of supermassive black holes. While stellar black holes are well understood, the origins of their supermassive counterparts remain elusive. How did these giants, with masses millions or billions of times that of the Sun, grow so large? Did they form directly from massive gas clouds in the early universe, or did they grow gradually by merging with smaller black holes and consuming surrounding matter? Upcoming telescopes, such as the James Webb Space Telescope, may provide insights into this question by observing the early stages of galaxy formation. The nature of the singularity at the center of a black hole is another profound mystery. According to general relativity, the singularity is a point of infinite density, where the laws of physics as we know them cease to function. However, quantum mechanics suggests that there must be a deeper explanation. Resolving this contradiction is one of the greatest challenges in physics and may require a unified theory of quantum gravity, a framework that combines the principles of quantum mechanics with Einstein's theory of general relativity. The black hole information paradox also remains a hotly debated topic. Although some progress has been made, such as Stephen Hawking's proposal that information may be encoded in Hawking radiation, a complete resolution has yet to be achieved. Solving this paradox could unlock new insights into the fundamental nature of reality and the interplay between quantum mechanics and gravity. Another area of active research is the potential connection between black holes and dark matter. Some theories propose that dark matter could be made up of primordial black holes, formed in the chaotic aftermath of the Big Bang. If true, this would provide a groundbreaking explanation for one of the universe's most elusive substances. Observatories like LIGO and Virgo are helping to test this theory by searching for signs of primordial black holes. The search for wormholes and connections to other dimensions also continues to captivate physicists. While these concepts remain theoretical, future technologies may allow us to test whether black holes could serve as gateways to other parts of the universe or even to alternate realities. Such discoveries would revolutionize our understanding of space, time, and the fundamental structure of the cosmos. Looking ahead, new instruments and missions promise to expand our knowledge of black holes. Projects like the Laser Interferometer Space Antenna, LISA, aim to detect gravitational waves from supermassive black hole mergers, while future iterations of the Event Horizon Telescope, EHT, will produce even sharper images of black holes and their surroundings. Additionally, advancements in particle physics and quantum computing may provide the tools needed to explore the mysteries of black holes on a theoretical level. Black holes represent the ultimate frontier in astrophysics, where our understanding of the universe is stretched to its limits. Each new discovery not only answers old questions, but also raises new ones, driving us to explore deeper and think more profoundly about the cosmos. As technology and science progress, the mysteries of black holes may one day reveal the keys to understanding the universe itself. Black holes are some of the most fascinating and enigmatic objects in the universe. From their immense gravitational pull to their potential role as gateways to other realities, they challenge our understanding of physics and push the boundaries of what we know about space and time. Throughout this video, we've explored how black holes form, the bizarre phenomena they create, and their profound influence on the structure of the universe. We've delved into the mysteries of the singularity, the tantalizing theories about wormholes, and the ongoing quest to resolve the black hole information paradox. These cosmic titans continue to inspire awe and curiosity, reminding us how much there is still to learn about the universe. As we look to the future, advancements in technology and science will undoubtedly reveal even more about black holes and their role in the cosmos. Each new discovery brings us closer to understanding the nature of reality itself and our place within it. The mysteries of black holes are a testament to the infinite possibilities that the universe holds. They ignite our imagination and drive our desire to explore the unknown. What do you think lies inside a black hole? Join us next time as we explore more mysteries of the universe.